Hello and welcome to another video. In this video we're going to be continuing on with the TypeScript 175 and we're going to be doing LCA of a binary search tree. And so you're given a binary search tree and you want to find the lowest common ancestor of two nodes in the BST. Lowest common ancestor is defined as the lowest node in T that has both P and Q as descendant, where we allow a node to be a descendant of itself. So for 2 and 8, let's kind of like, the easiest way to find an LCA is just find where the nodes are. So let's say we have 2 and 8. So here we have 2 and 8. We just want to draw a path to the root for both of them. And then the LCA is going to be the first point where they intersect. So here it is node 6. Similarly, for 2 and 4, we're going to draw 2, we're going to draw 4. And the first point where they intersect is going to be 2, right? That's where they meet. So that's that one. And there's another one where we have 2 and 1, so that's just going to be 2 and 1. And the LCA here is going to be over at the 2, right? So essentially you have kind of like two things that can happen. Either two nodes are on the same path, kind of like this 2 and 4, 2 and 5. Let's say we have 2 and 5. Essentially, if we draw the path from 5 in one color, like this, and the path from 2 in another color, you could see like the first point these two paths intersect are actually one of the nodes. That could happen. Or they will just intersect at some other point. Like let's say we take 0 and 4. So these will intersect at, not at one of them, but at a mutual point, so like this. But essentially, it kind of boils down to the same thing. The first point where both paths intersect, the lowest for one down, is going to be your result. So we could do this. I'm going to discuss like a trick you could use for binary search trees that is going to make it faster to find our answer. And we're just going to go through this one and look at some examples. So we're actually gonna just keep reusing this example. Maybe we can make it a little bit bigger. So let's do that. Let's bring it down here and let's make it bigger so our tree is bigger. There we go. And we're just gonna keep reusing this and we're gonna try this with like different nodes and see what happens. So let's say we try to have like 0 and 9. So essentially, starting at the root, there's only a few things that can happen. So either let's actually be at the root and let's write our 0 and 9. So our root's over here, 0 and 9's over here. So essentially, there's a couple things. Case 1 is the nodes are on different sides of the value we're currently at, right? So we're at this node here, and the two nodes we're looking for are on different sides. In which case, if you think about it, what would be the lowest common ancestor if they are on different sides? If we actually have a node where the nodes are on different sides. So let's take a look. If we draw our paths, that would be the LCA now, right? So when the nodes are on different sides, that node that we are on is actually the lowest common ancestor. Now there is another possibility. So let's say instead of picking 0 and 9, we pick 0 and 3. Now they are on the same side, right? So they are on the same side. So if they're on the same side, we know exactly where to search, right? Like, why would we need to search all of this? We don't. And it's very easy to know what side they are on because we can just compare the values, right? So if 0 and 3 are less than 6, similarly for the different sides, we know what side of the tree these nodes are on because we can just compare the values, right? Values that are bigger are on the right, values that are smaller are on the left. So these are both on the left. So now we can just go left and we can do it again. So we go left and then we compare again. And so here they are on different sides, right? 3 is to the right and 0 is to the left. And let's find the LCA now if they are on different sides. Well, if we draw a path to the root, you can see they intersect at 2. So 2 is the LCA again. So you could see like no matter what, whenever your nodes are on different sides of a node, that's going to be the LCA. Now, there is one more kind of like thing that we forgot to mention. Let's say we have 4 and 5 as our nodes. So, and this is where we have a little like thing that we didn't account for. So here they are on the same side, so we are going to go left. Here they are on the same side again, so we're going to go right. So this is our last case that we didn't really account for. So if one of the nodes is the node we're currently on, and another, basically, as soon as we run into one node that is either P or Q, then that is our LCA, because that's going to mean that our path is going to go through this, right? And so if we draw our path again, right, so the path for 5 is going to go like this, and the path for 4 is going to go like this. So the LCA is actually 4 because that's the first node they intersect at. So those are kind of our conditions, and luckily we can actually handle different sides and one of the nodes being the node we're at the same way. We can simply check if the nodes are on the same side, then move our node. Otherwise, we found the LCA. So if we go back to our first example, this one, right, where the nodes are, let's say, 0 and 9, they are on different sides, but they're also, the key is they're not on the same side. So that is handled. And then if we go to our other example where let's say we have like this 2 and 5, and so here they would be on the same side, and then here they would be on, yeah, so here they would be on the same side, so you'd go left, and then here, this is kind of like, they're not on the same side, they're not on, they're not, basically, they're not on the same side, right? So if they're not on the same side, because this is not on the side, like this is one of the nodes. So if they're not on the same side, which is true in this case, then we found our LCA, and we did indeed, right? So this would be our LCA here. If this is our, like, this is the thing we need to be returning. And so that's pretty much all we have to do, is we just simply have to check if both nodes are on the same side, like if both nodes are greater than the value or smaller than the value, let's traverse that way. Otherwise, that is our LCA. And so we're saving a lot here because we're only checking like the relevant path. We're not going to like every single node in the tree. So we're actually saving. In worst case, you're still not saving anything because let's say you have something like this. So if you have like 0, and then you have like 1, 2, and so on, so on, 99, 100 maybe, whatever. And your P and Q are 99 and 100, then you would actually have to like recurse all the way down here. So that would still be O of n. Well, not recurse, but you'd have to like get here. We're actually gonna, in the rare case here, use an iterative solution instead of a recursive solution because it'll be a little bit faster. I'll kind of show you why. But yeah, we're in practice, we're going to be saving a lot. In theory, we're not going to be saving any time, but we are going to be saving space, and I'll show you how to do that. So that's going to be the optimization with a binary tree instead of just doing a manual search through all the nodes that we're going to be doing for the next problem, which is just LCA of a generic tree, which we'll do tomorrow probably. So let's code up this one. So let's actually full screen. Okay, so we're basically going to say while. So actually, we can just use while root here technically, or while node or whatever. This should technically never leave the loop, so this will always return before the loop's over. But so we can even have like a while true, to be honest. It'd be fine. Yeah. So we could have a while true, and then in here we can say if p.val is less than root.val and q.val is less than root.val. So if they're both on the left, what do we want to do? We just want to go left, right? So root equals root.left. So we just want to go left. And if they are on the right, so if p.val is greater than root.val and q.val is greater than root.val. So if they're on the right, we want to go to the right. So root equals root.right. Otherwise, we found our answer. Because they're either going to be on different sides, in which case it's still LCA, or one of these will be P and Q. So you can check if you wanted to, if this is still not clear to you. You can check if you ever run into P or Q, that is your LCA. But this will kind of handle it for you. Because, yeah. So this is Q. Yeah, let's see. There we go. Okay, and this is as efficient as it gets, as always with TypeScript, so just all over the place. But anyway, so let's go through the time and space for this one. So, like I said, worst case scenario, your tree is completely in one direction, right, which will be O(n) time. But now we are saving space because we're not recursing. We have an iterative solution without a stack or anything. We're simply just changing our LCA potential value. So the space is going to be O(1) because we are not recursing anymore. So that is saving something there. And yeah, I think that's going to be all for this problem. So hopefully you liked it. And then tomorrow we're going to be doing generic LCA. And obviously, if you could up a generic LCA, this would work for this problem. But this is like the optimization you can use for a BST. And if you didn't think of this one, you could also do slight optimizations, but they're not going to really affect time and space, where you could still check for these things in a recursive solution and not go the right sides, right? So if you're at some node and you're recursing and both of your values are on the left, you can just say, like, let's just not go to the right. But worst case scenario, that's still going to be O(n) time and space. It'll just run faster on LeetCode. But yeah, that's going to be all for this one. So hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.